previously defined this term potential energy as being an integral of the work done by a force over some interval in space. Since the potential energy is defined in terms of the integral of a force, we can flip that relationship around, and given a potential energy, like as a function of uh, one spatial dimension, we can take that potential energy curve and turn that into a force. Uh, so the way that turns out is force is a function of one spatial dimension x. It's going to be minus the derivative of the potential with respect to x. The easiest way to think about this, at least at first, is imagine you have a bowl and a marble. If the bowl is set to be concave up and I place a marble inside the bowl, it's going to roll downhill, right? Um, that means I'm looking at the slope of u as a function of x. It is a negative slope, and I will get a force to the right. Okay. After the marble has passed the lowest point in the bowl, it's going to start to roll uphill and slow down, slow down, slow down as it goes. Okay. That's telling me that I have a force. There's a positive slope along the tangent to the bowl. A positive slope with that minus sign gives me a force that points to the left. So the marble is going to slow down, slow down, slow down, and just come to a stop when it was at the same height that it initially started at. The other thing I can think about is take the bowl and flip it over. And now I'm going to set marbles on the top of the bowl. Okay, so now the marble here on the left, the slope is positive because the potential is increasing, right? That means I'm going to have a force that points to the left. So the marble, as expected, is just going to roll off the bowl and go very, very far away from where it started. And if I go past the highest point on the bowl, the marble is over here on the right. Now the slope is negative. All right. That derivative is going to be negative, but I also have a minus sign. So I'm going to have a force to the right. And the marble is going to roll off and go faster and faster and faster, and then roll all the way home. All right. So in between those points, right, is where the potential has no slope, right? Those are special points that we're going to talk about in a little bit. Those are points of potential equilibrium for a given potential curve. So we've got the force telling us, or the slope of the potential is telling us the directionality of the force. And the next thing we want to talk about is not the first derivative, but the second derivative, whether a potential function is concave up or concave down. All right. So equilibrium points for these two bowls, and whether they are stable or unstable. So the equilibrium point means the point where the derivative vanishes. So for a bowl with a normal orientation, the derivative of the potential vanishes there. And then if I flip the bowl upside down, again, the derivative vanishes there. Okay. So those are our equilibrium points. If the bowl is concave up, okay, so I'm at a point where the first derivative vanishes, and the second derivative points, second derivative is positive, so it's concave up, points up. Then that is a point of stable equilibrium. And intuitively, if we're just keep running with our bowl analogy, if I push the marble a little bit to the side, the restoring force has it roll back towards the point of stable equilibrium. So that's how we can tell that that is stable equilibrium. The other equilibrium point we could have is unstable. So this is where, again, it's a point of equilibrium because the first derivative vanishes. The second derivative is negative. And it's a concave down function at that point. And unstable meaning that if I take the marble, I balance it just right at the point of equilibrium, I could potentially do it sort of like getting the pencil to stand up on its tip. Could be done, unlikely. But then once it is done, any small perturbation is going to cause it to move away from the point of unstable equilibrium. So if I could get the marble to just balance there on top of my bowl, it is going to roll right off any little perturbation. Now let's take those ideas and apply them to a somewhat artificial, but possible potential curve. So I have a curve here. I will call it u as a function of x. And this variable is going to be x. And let's go through and label what we can for this. So my function is going to minus infinity really fast as I go to 0. The function is steeply increasing, and there is a point where the first derivative vanishes. Come through. There's another point where the first derivative vanishes. And another. And another. And I tried to draw this so that you could see that it was changing from concave down to concave up. So the function goes through an inflection point here, right? But that's not a point of equilibrium, okay? Because if I perturb this to one side, it's going to go far away. Perturb it to the other side, it's going to come back, right? So it's not an equilibrium point as these other ones are. So it's possible to have an inflection point for your function. And let me go ahead and clean that up so we don't have to worry about that. All right, so out of those, which ones are going to be stable equilibrium and which ones are unstable? Well, if the function is concave up, it's going to be stable. So here's a point of stable equilibrium. That is a point of stable equilibrium for either one of those. If I perturb the object, the force corresponding to this potential is going to push it back to the equilibrium point. And then I've got two unstable equilibrium points. So it's just going to label those with U for unstable. So those are points where the function first derivative goes to 0, second derivative is negative. So it's concave down. All right. And then the other thing that we want to talk about is the idea of a turning point. So if I give a particle, say it's in this potential, and it's right here at one point in time. So it has some amount of kinetic energy and it has some amount of potential energy when it's at that location, that particular value of x. And if it was initially moving to the right, it's going to keep going to the right. And the kinetic energy is going to decrease, right? Until the kinetic energy goes to 0, because now I have just enough energy to match the potential energy at that point, because there's no gap anymore, right? I'm not above the function. So the particle would go to the right, This whole time, so slope is positive, so it's feeling a force to the left. It's going to slow down, slow down, slow down, slow down, and then it reverses direction if it's a conservative system. And it's going to come back, and now it's going to do the same thing going to the left. Use up all the kinetic energy so that now all the energy is potential. As it was going to the left, the slope is positive. No, slope is negative, sorry. So minus a negative is a positive is a force to the right. So it's going slower and slower and slower and slower and slower, comes to a stop for a second or an instant, and then reverses direction. So all this particle can do is just bounce back and forth at the same energy level between those 2 points. So those 2 points are called turning points. So given a potential energy curve, and if you have a system, so a particle experiencing that conservative force, then we could think about the motion of that particle is just bouncing back and forth between turning points. If you change the kinetic energy, those turning points could change. So if I give it enough kinetic energy, they can be all the way up here. And it has a much more complicated excursion. It's going to go between this turning point, the far left, to this one on the far right. Now, sometimes it's going to go faster. Sometimes it's going to go slower when it's only this energy difference, right? But eventually, it's going to come to the point where all the kinetic energy is used up. It's all potential, and it reverses its direction, and it goes back. Right? So points of stable equilibrium are where the potential has a zero in its slope and it's a positive second derivative. Points of unstable equilibrium are points where you have zero for the slope, but it's negative for the second derivative, concave down. I could have an intermediate point where the slope goes through a zero, but the second derivative is flipping signs on either side. It's an inflection point that can happen. And then turning points are where for a given amount of kinetic energy, I have a particle that's going to be bound by the potential. It's just going to bounce back and forth between the turning points. So the term lives up to its name. So this is kind of an artificial looking potential curve, but these do come up in physics quite a bit. Most all of the interaction of matter, in that matter is made out of atoms. Those atoms are weakly attracting one another when the atoms are close, but not too close. But they will strongly repel one another when the atoms are close, right? They can't pass through each other. So you have a force that is weakly attractive becoming strongly repulsive. And you can model that force very well. It's called Leonard Vickert potential, or as like a 612 potential is what it's often called. It's a dipole-dipole interaction. So these sorts of potential energy curves have a lot of utility in physics.